Well, hello everyone, and welcome to Inferential 2. This is a two-sample t-test. So first let's look at choosing the appropriate statistical test. The quality control department of a paperclip manufacturer periodically tests the quantity of their packages. They want to verify that packages are being filled to the advertised quantity, which is an average of 250 clips. They take a sample of 30 boxes to determine if they are being over or underfilled. They find that the 30 boxes have an average number of 251 paper clips with standard deviation of 0.8. So what test should they conduct? Well, let's see. Do they have the population standard deviation? And the answer is no, so it's a t-test. And the direction of the test is two-tailed, since they don't know if it's overfilled or underfilled. Kroger knows that historically the average customer spends $52.53 on an in-store purchase with standard deviation of 28.29. Workers have noted that pickup orders tend to be more expensive. Kroger wants to test this observation using statistical analyses. They take a sample of 100 pickup orders from the past 3 months and find that the average is 70.21 with standard deviation of 24.56. So what kind of test? Well, the population standard deviation is known, so it makes it a z-test. And the direction of the test is more expensive, so more means right, one-tailed right. An advertisement company is pitching a new print ad to one of their clients. They know that the client's previous print ad received a rating of 6.4 with a standard deviation of 1.2 on a 9-point scale in consumer research. They want to determine if the new ad is different from the previous. They take a sample of 50 and have them rate how appealing the print ad is. Alright, so different is the key word. That makes it a two-tailed test, and the standard deviation is known. That makes it z. So z, two-tailed. And finally, IKEA has modified one of their popular furniture pieces, and they believe the assembly for the updated piece is faster. Previously, the average assembly was 63 minutes. They recruit 20 workers and observe the time it takes them to assemble the updated piece. They find that the average for 20 workers is 55 minutes with standard deviation of 10. And this hint here says faster means less time. Right, so faster is less time, less means left, so that's going to be a one-tailed left test. The population standard deviation is not known, so that's going to make it a t-test, one-tailed left. Alright, so all of this was review. This was review of stuff that we have done before, because these are all one-sample tests. Alright, now we're going to move on to two-sample tests. So here we go. A software development company wants to determine if a new interface design changes the average time it takes users to complete a specific task compared to the old UI design. To investigate, the company randomly selected users and presented them with either the new or the old UI. Their completion times were recorded. At the 5% significance level, can the company conclude that the new UI design changes the average task completion time? Assume that the population variances are unknown and unequal. Alright, so what's different about this? What's different is that we get two sets of data, the new and the old. The new is also called the comparing group, and the old is the reference or benchmark group. Alright, so we're trying to see, is new different than old? Now you could say, well, isn't that what we were doing before with the one sample test? Yes, that's true. But on the one sample test, we didn't have this data. This was already assumed to be, the summary of this data here was assumed to be known and have known statistical properties, the mean and standard deviation. Now, all we've got is a sample, so you have two samples. So we're after, are these two samples similar enough that they could have come from the same population? And that's the key to this test. In fact, if you look over here at the chart, what you'll see is that what fills the chart now are not x bars, but delta x bars, because what we're really looking to see is this is a plot of the differences of two means that come from the same population. So it's the difference of two means if those two means come from the same population. And if you're way out here, then is it possible that you came from the same population? Yes, but we're going to reject you nonetheless because it's very unlikely. So that's really what we're looking for again. Are we in the tail? Okay, so what's the correct test? It's an independent samples t-test. The reason it's called independent samples is because these aren't paired samples. We're not taking the same person and saying, hey, you, try this one, and you also try the other one. These are two different groups of people. Otherwise, it would be a paired sample test. So that's why it's called independent samples. T-test, it compares two sample means to see if they came from the same population. So, two sample t-test. We're testing the difference in sample means, thus we will use the sampling distribution of sample mean differences. In fact, differences really should be bold-faced there, right? Because that's the delta x bar. Before it was sample means, the distribution of sample means, now it's sample mean differences. And that's going to be a t-distribution. And since it's differences, right, it's the differences in the means, it's this one. And that brings up all the equations associated with that. Okay, this is a two-sample test, which compares two samples to see the likelihood that they belong to the same population. By convention, the mean of the comparing group is called x bar 1. Which sample is the comparing group? In other words, which one is x bar 1? And you can actually look here and see there's comparing, which is new, x bar 1, new. So new. And by convention, the mean of the reference group is x bar 2. Which sample is the reference group? Well, it's going to be old. So that's all that's left. The null hypothesis states that the two groups have the same population mean. What is the null hypothesis for this test? Sample means are the same. The alternative is that they are different, but let's see, are we predicting a direction? All we were looking for is changes the average time. It didn't say what direction that was. So, just different. And that means it's two-tailed. Okay. Now over here, now all these stats in previous problems with the one sample test, we were given for one of these groups, we were actually given, actually for the reference group, we were actually given the stats in the problem. We aren't now. We have to calculate every stat. So let's do it. So the average for new average for alt, All right, so what this whole problem comes down to is, could you have taken two samples from the same population and have one sample come out at 5290 and one come out at 5517? And obviously, that's going to depend on how many samples are in the, how many observations are in each sample, and it's also going to depend upon the variability that's observed in these samples, because that variability is going to be assumed to be in the populations as well. So let's keep going. So count new, count hold, and standard deviation, which, remember, this is a sample, so it's .s of new, and of hold, standard error. Okay, so how do we compute the standard error? It's going to be different than before. And the formula is sitting right over here. It's going to be the square root of s1 squared divided by n1 plus s2 squared divided by n2. We're going to have to use lots of parentheses to pull this off to make sure that all the operators stay with what they're supposed to stay with. So square root, open parentheses, then we'll skip a space just so we can keep our parentheses straight. And first we pick s1 squared, so it's that squared divided by n1, then a plus, open parentheses, s2 squared divided by n2, close that parentheses, close the outer, and that's our standard error, which notice is taking into account, in a way, kind of the average of those two standard deviations. Modified obviously by the sample size of each. Okay, and then we're at 5%. Alright, and we'll split the 5% since it's a two-tailed test, right? We decided over here it was two-tailed. So we'll split the 5%. Alright, and then we have, now, it's a t-test, and you need degrees of freedom on a t-test. Before, it was really easy to get the degrees of freedom, because you just took the sample size minus 1, but if you look at this formula, which we've given to you, you don't have to type it, it's a lot harder to get the degrees of freedom on a two-tailed test. Sorry, two-sample test. So that ends up being 17, and you'll notice that if we added these two together, 10 and 12, that would be 22. So it's definitely not 22 minus 1, and it's not even 22 minus 2, right? It's just not that simple. You've actually got to go through this formula to get degrees of freedom. Okay, but we're not going to make you do that. I just gave you the formula. All right, so now we calculate the t-score. T.inv, that probability, and there's our degrees of freedom. Same thing here, T.inv, except it's not just that probability, it's 1 minus that probability, because it's on the other side, and the degrees of freedom. And then this pretty much stays the same. We take the t-score times the standard error. And then what we would do normally is we would add that to the mean, right? But if you look at it here, the mean is 0, so kind of no point in adding it to the mean, so it's just going to be that. And then again. So those are our critical values, both as t-scores and as raw scores. And remember, the raw score is the critical value of how much difference would be allowed between the two means. So now let's look at our test statistic, and let's look at, first of all, what actually is our difference. We know how much is allowed now, but now let's see what kind of difference we have. So we'll take the new minus the old, and so our difference is negative 2.27, which sure looks like it's more than would be allowed, right? Because that'll be more extreme than the negative 1.68. But let's finish this off so we can see that plotted here. Make sure that's true. And calculate the t-score, which is going to be x. Well, let's see what the t-score is going to be. So we're going delta x bar to p of x bar, and t is going to be delta x bar divided by the standard error. So, oops, I messed up already. Equals delta x bar divided by the standard error. And if you think about it, before it was always x bar minus mu, but mu is 0. So it's just delta x bar divided by the standard error. And then what's the probability of that? It's going to be t dot dist of that t-score with that many degrees of freedom and true. So we are out here. Negative 2.27, as we suspected, is to the left of negative 1.68, and it's in the rejection region. So in other words, the difference between these two means is too big for them to have come from the same population, which means that we're going to say they came from different populations, which means there really is a true difference between the comparing group and the reference group, a true difference between new and old, which is kind of what we were testing for, right? So there is a difference, and in this case, it's a good difference in the sense that it's taking less time for users to use the new UI to get stuff done. All right, now let's go with our margin of error. Remember the formula here. Margin of error, t dot inverse 1 minus alpha divided by 2. So that's effectively the right hand on a two-tailed test. It's the right hand value. So we know it's going to be this guy, so we can just use it. Equals that times the standard error. 1.68. And then start again with delta x bar, which is this number, and then take that number plus the margin of error. Well, that didn't work out well. Let's try that again. Undo. Equals that number plus margin of error. I don't know what I did before, but anyway, everybody's happy now. Equals equals that number minus margin of error. And that gives us our confidence interval. And you'll notice the confidence interval does not pass over the mean, which is further evidence that they come from different distributions. For the p-value approach, you compare the p-value, or p of delta x bar, to alpha. In a two-tailed test, alpha is split in two, 1/2 of alpha for each side. So we use alpha divided by 2 as a comparison value. What reference value are we using for the test? There it is. Reference the p-value. Is our p-value bigger or less than alpha? It's less than alpha. Remember, it's p of delta x bar, less than alpha. So we're going to reject. Alright, now we'll do the same thing, but with the critical value approach. So we'll reference the lower critical T score and the upper one, and the test statistic 1. And it is more extreme, so we're going to be in the rejection zone. We reject the null hypothesis. Alright, more conclusion and interpretation. If you fail to reject, then your conclusion, right? If you reject, then you're saying they're different. And we are saying that they're different, and that this one is less, right? So mu new is significantly less than mu old, which is a good thing because less means less time. What's the conclusion in symbols? Mu new is less than mu old, and if you reject the null hypothesis, then the test is considered statistically significant. If you fail to reject, the test is considered statistically non-significant. What are the results? We are statistically significant. Okay, we're almost there. So even if the true population mean difference is 0, we would still expect that any two samples would have minor differences due to sampling error. What is that sampling error? So we'll reference the value. And now from the empirical rule, we're after the 95%, which remember is -2 to +2 standard deviation. So what's that? It's going to be -1.59 to 1.59. And what Raman difference is the cutoff for rejecting the null? And since we're rejecting on this side, it means it's going to be the lower one. And it's going to be that one since it's after raw value. And what's our actual sample mean difference? So that's delta x bar, which is this value here. And what are you estimating with the confidence interval? You're estimating the difference between the two populations that these two samples came from, assuming they came from two different populations. And what's our interpretation of the confidence interval? It's going to be that we are 95% confident that the population mean difference is between -3.95 and 0.59. So there's the -3.595 and 0.59. no, sorry, negative 0.59. And as you can see, negative 0.59 falls short of the 0 point, which is why, again, another data point for why we reject the null hypothesis. And we're done with this one. We'll see you in the next video.